How do I remove this? Okay, excellent. Okay, so let us talk about some theoretical concept behind this membrane process, right? So as you know, the membrane is a porous medium which allows selective transport of some molecules through this layer or through this region. Typically, the flux or the solvent rate, or let us say the permeation rate or the filtration rate, is given by the Darcy law. Almost, I believe, all of you have some, at least you have heard about this. Like Darcy law is typically used to describe the flow in a porous medium, or is to describe the flow field or the velocity field in a porous or a semi porous region. And what is the law? That tells you that the velocity of the fluid velocity or the solvent flux is proportional to the negative of the pressure gradient. This is the generalized, the Darcy's law or the typical Darcy's law. For any interest, if anyone of you is interested to look more into how this Darcy's law was fundamentally conceived from a more, initial stage, you can look into this. If you just Google it out and see that how the Darcy law could be derived from the Navier-Stokes equation for a porous medium domain, right? But that's a very rigorous exercise and something I think we should not do in this class, right? It's beyond the scope of this class. But if you're interested, you can look into that. You can just do a Google search and you can find it out that how the Darcy's law is actually derived from a more fundamental standpoint, right? But we will take it from here. So this velocity field U, so the underscore that I have written below this is U is to denote that U is a vector and not a scalar quantity, right? So this U is proportional to the gradient of the pressure. Now, typically for the membranes, these are very, very thin, domains, right? So typically a membrane, or essentially the porous region of the membrane, may be around 100 micron or 200 micron, or even less. In fact, 200 micron is the entire thickness of the membrane, right? Which is like just like a paper. So the essential region of the porous part, or which actually does this selective separation, even further less, or maybe in few nanometers, I would say, right? So in this small region, instead of the pressure gradient, a more appropriate thing, or trying to find out that how pressure changes with the across the thickness of the membrane, a more practical way to write this delta P is something in terms of delta P by the thickness of the membrane, right? So what is this delta P? Delta P is just the arithmetic difference across the two sides of the membrane, and you divide it by the thickness of the membrane. So instead of writing a gradient, we just do this sort of finite difference approach, because the thickness is really small for this domain, right? So and the next question is that how to remove this proportionality constant. So typically that's how the concept of permeability is evolved. You write it in something like this, a sort of like this. So typically you can write this, this K is the permeability and mu is the viscosity of the liquid. So typically this permeability has different, sort of description in different domains, in different fields. Like civil engineers represent this in some different units. Geological people represent this permeability in different way. Mechanical people write this in different way. We chemical engineers also try to write this in different ways. So this entire thing in the context of the membrane, science, and you can easily work out what would be the unit of this permeability K, right? So this entire thing is generally written down as LP. right? So it's sort of a, you know, a term which clubs together all this K, mu, thickness and all, and you write this together in terms of the LP of the membrane, right? So this LP is one of the, I mean, all these are essentially constants, right? K, mu, and Tm and all. So this LP defines, I mean, higher is the value of your LP, the more permeable is your membrane, right? With lower pressures, you can achieve significant amount of flux or flow through the membrane, right? So higher is the LP value of the membrane, the more porous it is or more permeable it is. That's the general idea, right? You can also write down this LP or this permeability in terms of the resistance. So another common way of writing this LP is 1 by mu Rm divided by delta P, and you can easily work out what is this mu Rm. So this Rm is nothing but Tm by K, sort of like this, right? So this is like the membrane resistance. So if you want to replace this permeability in terms of some sort of resistance to the transport, you can write this as Rm instead of you know, LP. So you can also write this 1 by mu Rm by and into this delta P. So this is how typically we write this you know, form of the Darcy's law. And sorry, I do not want to distract you, but just I want to have some more slides in the backup. So this is how we write this Darcy law to describe the flow through the porous medium, essentially in this case the membrane, right? This delta P, a more technical jargon, is known as the trans membrane pressure drop, which is nothing but the difference of the pressures across the two sides of the membrane. One is the feed side, one is the filtrate side. So is there any confusion on this part? On this Darcy law? Because this is one of the very fundamental things to describe the flow or the rate of permeation or the filtrate rate through the membrane. Now, please note, I mean, this is a discussion we had also before. This delta P is the net driving force in this case, right? And we are all talking about pressure different, you know, pressure driven separation process. So naturally, it's the pressure that plays a role. We're not talking about other, you know, types of forces that dominates the chemical potential. It's essentially the pressure. In this case of the pressure, it is the net pressure that, or the net difference in the pressure across the two sides. So now if you have very small solutes to be separated, let us say you are having a RO type process, then you will be having very small solutes, essentially the salt molecules, to be separated, and the salt, these small molecules essentially have large this osmotic pressure, right? So osmotic pressure plays a big role in this case, right? So it's, and also it's not the osmotic pressure of the solution or the osmotic strength of the solution, it's the difference of the osmotic pressure across the two sides of the membrane, right? Similarly, as we write, delta P is equal to P on the feed side minus P on the filtrate side, right? Another important point is the delta pi, or the difference in the osmotic pressure. So that is pi on the membrane side minus pi on the filtrate side, right? So the net driving force, this U, whatever we are talking about, is equal to minus, let us absorb the minus sign inside now. And since we are talking this delta P in terms of P feed minus P filtrate, so it is, the flow is in the direction of the decreasing pressure side, right? So let us absorb that minus sign in this way, because we define our this pressure and along the direction of the flow. So this would be something like this in this case. Is the difference of the osmotic pressure across the two sides of the membrane reduces the net driving force. So it's not delta P or not the mechanically applied force that has that will decide what is the rate of filtration. It is the difference of the driving force or the excess driving force over the osmotic gradient or the osmotic difference, right? That's how we typically write this delta P minus delta pi. Is this clear to all of you? So think of this system where you have, let us say, this is a small membrane we have, and this is the feed side. So feed sides, the solutes are retained over the membrane surface, right? So this is the feed side, and this is the permeate side where the concentration of these solutes is significantly less or close to zero, right? So in the solute side, so in the filtrate side, which is typically represented as Cp, right? Cp is nothing but concentration of the solutes that is separated in the permeate side, and this is generally written as C0 or the bulk concentration, and over the membrane surface we write as Cm, right? We'll talk about these nomenclatures, but just have a look into it. I mean, just have an idea about the different names of the variables. So delta pi, this delta pi, what we write is a function of Cm minus a function of Cp, right? And since Cp is significant, very close to zero, so this part almost goes to zero. So delta pi essentially becomes a function of Cm. For lower molecular weight solutes, if you recall your thermodynamic classes, how osmotic pressure depends on the solute concentration, you will see that you can have a virial type coefficients, or you will find that the osmotic pressure, right, osmotic pressure for lower molecular weights solute is typically linear in the low concentration zone, and when it becomes significantly higher, then it becomes like slightly non-linear type of variation. But there is a significant zone, right, significant zone of the osmotic pressure where it follows a linear trend, and this zone of the linearity decreases. This lone zone or the of the linearity decreases as the molecular weights of the solute increases, and its concentration also, I mean, this sort of the osmotic pressure also decreases. So for something like this, it would be, so the molecular weights of the solutes would be increasing along this direction. I hope I am clear. So as the molecular weights increase, the osmotic pressure reduces. Not only that, this zone of linearity of the osmotic pressure with the concentration also reduces. I mean, the range of the concentration over which the osmotic pressure varies linearly with the concentration is also small. That zone is also small, right? And typically, if you operate with these salts, for this case of reverse osmosis, you will find that this zone of linearity of the osmotic pressure with the concentration is to a significant concentration, right? So for all practical purpose, you can consider this delta P, sorry, this delta pi as some constant multiplied with Cm. Okay, so this is how you can typically write your delta pi, because Cp is 0 and alpha is a linear constant that follows the osmotic pressure with the concentration, and so concentration is the concentration of the surface that is known as Cm, right? If the solutes are large, we'll talk about this in more detail. If the solutes are large, they deposit and foul the membrane surface. Right. We'll talk, of course, in detail, but just to give you a small picture, I don't know if this is a good one. Yeah, something like this. So you see that the solutes tend to get deposited over the membrane surface if they are larger than the pore size of the membrane, significantly larger than that, right? And they will form like a gel over the membrane surface. So now this gel acts like a dynamic membrane over the surface of the membrane, or let us say a dynamic layer over the membrane surface, which adds or which offers additional resistance to the transport of the solvent or to the filtration process, right? So this leads to the formation of the gel, right? And this adds resistance to the transport. So since the molecules are large, osmotic pressure is not so significant, not so important. But now you have a formation of an additional layer over the membrane surface, or it blocks or fouls the membrane and reduces its capability of the filtration. In other words, it adds to the resistance to transport, right? So in this case, the solvent flux or the flux through the membrane or the velocity is written as in terms of the resistance formulation. So typically we have this delta pi by mu Rm, right? So in this case, we have an additional resistance. Similar to Rm, this Rg is something that can also be computed as a part of the filtration, and this Rg, of course, depends on the thickness of this gel layer. What is the porosity of this gel layer? What is the solutes or the intermolecular solute interactions, solute membrane interactions, all these factors play a role. We'll of course talk about it in detail. Size of these molecules, size of the molecules relative to the pore size of this membrane, all these factors affect the value of this Rg. But please note one thing, that during a particular filtration process, in both the case, in the case of the osmotic, where the osmotic pressure is important, or well, whether this formation of the gel or the membrane fouling is important, right? In both the cases, right? Let us say in the case of the osmotic pressure, the membrane surface concentration increases with time as the filtration proceeds with time, isn't it? Because as you continue to do filtration, the solutes that are getting separated will be on the membrane side or will be on the feed side. So they will either deposit over the membrane surface and it will impart a significant resistance if they are large molecules. If they are very small molecules, that may not be so important and it may not at all form a gel. So when does it forms a gel? When the concentration over the membrane surface, let's look into this example. When the concentration of these solute particles over the membrane surface exceeds its solubility limit, isn't it? In this region, when it exceeds the solubility limit, it will try to precipitate and leads to the formation of the gel, isn't? That's when this gel forms. Now, in the case of the salts or lower molecular weight solutes, it's most likely that its solubility limit is quite high. So it may not directly, starts to form this sort of gel-like semi-solid region, or it tries to precipitate. It may still be in a dissolved state, but the concentration on the surface of the membrane would be significantly high, and that would affect the viscosity locally and all those things, right? But it may not form a gel. Or a gel is like a physical, semi-solid region or a semi-solid layer, in fact. Okay. So in both the cases, when you have the osmotic pressure to be important or when you have this formation of the gel to be important, both these effects increase with time, right? Because as the filtration goes on, the membrane surface concentration will continue to rise, right? So in the case of osmotic pressure the osmotic pressure difference would also continue to rise, and as a result, the flux would also continue to decrease, isn't it? Because if the osmotic pressure is increases of the solution, and that could only happen if the membrane surface concentration increases, isn't it? If you just go back to the this thing here, if Cm increases, let me write it here, for osmotic pressure controlled system, if Cm increases, not if, with time, Cm would increase, and that means delta pi would also increase, and that means this U would go down. Similarly, for gel controlled system, right, the gel layer, let us say this Rg is a function of the solute particle diameter, the thickness of the gel layer, thickness of the gel layer over the membrane surface. Then I would not write, I will write dot dot here, because there are other parameters like solute interactions, porosity of the gel layer, I can write that, phi g, right? All these parameters affect, and it is a function of that, right? So in simple words, the particle diameter or porosity of the gel layer will not change. It's generally the thickness of the gel layer that changes, and it will continue to be more thick and more thick, and it's the zone of the gel layer would expand and it would grow, right? And of course, since this is the physical layer of a semi-solid or almost a solid region, it will also reduce the flow channel thickness also, right? Anyway, so with time, the thickness of the gel layer, let us say Lg, would increase, and that means the resistance offered by the gel region would also increase, right? And ultimately, it means the flux or the transport rate or the filtration rate would drop. Right? So in both cases, I mean, these are the two extreme cases that I have told you. Like one is the osmotic pressure is important, and where the gel formation is important. In both these cases, you will see that with time, there is a fouling of the membrane surface. This is what is known as fouling, right? Because there is a deposition of the solutes over the membrane surface. There is blockage of the membrane surface. There is additional resistance produced, or additional resistance to the transport rate. So in all these cases, the net impact that you see is the drop in the flux. So the flux would decline with time. And this is one of the classical problems in membrane science, that this fouling or this this problem due to the additional resistance is sort of necessary evil, right? Because to achieve a separation, this phenomena can't be avoided, right? You cannot avoid this phenomena of solute deposition or solute accumulation, the solutes which is getting separated over the membrane surface. That is not possible to avoid. All right. So this problem of flux decline is one of the biggest, I would say, bottleneck from engineering perspective. But without this, you cannot even achieve the separation, right? So there are significant efforts being made to reduce its impact, right? So what comes in your mind when we say that what could be the possible strategies to reduce the effect of this fouling on the membrane separation process? Can all of you just speak out loud, or you can write in the chat box maybe? What do you think could be a possible, or could be the possible strategies to reduce this effect of solute accumulation, or this increase in the concentration over the membrane surface? That is the problem, right? Increase on the concentration of the solutes that is getting separated over the membrane surface creates this whole lot of problem. And it is true for all types of filtration involving membranes, except for gas separation. There is the things are a little bit different. But for all other types of liquid filtration process, it would somewhere come within this zone, right? And this problem of zone means in between, either it's osmotic pressure controlled or gel controlled, or some solute layer, solute effects, solute based interactions taking place. Some sort of these would be taking place, and the net impact would be drop in the permeate flux. So if you have a pure water, right? So if I try to draw this, if I try to draw a plot of flux with respect to time. So in the case of pure water, it would be always constant. Right? But for all other cases, it would start, theoretically, it should start from this point and it would decrease. Higher is the concentration, more is the flux decline, and the net flux decline is lower. Right? So this is the general trend. So this is the theoretically possible limit of the flux, and as we can maintain up to that limit, it is better. But in most practical cases, this doesn't happen. It's always declines. Now, whether how fast is the decline or how much is the decline based on the concentration and other effects is something a matter of research and application. But it decreases. That's the fact. It's not possible to avoid. You can minimize the impact. So now I just put a question to all of you, that what do you think could be possible ways, since now you have some fair idea about what is a membrane, what do you mean by a module in a membrane, or how does a membrane structure looks like, how a membrane is fabricated or manufactured. So can you think of any strategies that would reduce the impact of this effect? Anyone? Tridipta? Others? Not here. Who else? Anyone? What do you think? Please write, all of you, please write in the chat box. Maybe that's preferable to, collate your views and get a collective opinion. Can I request everyone to write in the chat box? Maybe some possible ways to mitigate the impact of this fouling. Okay. Any kind of flow, okay, Tridipta. Varun wrote periodic removal of the deposit, passing fluid in the opposite direction. Aditya, what do you think? Tanmoy? Come on, guys. Others? Shashank, Yash, Vivek. We could be pre-treated, Shashank. Okay. Pre-treated for what? To remove the solutes? I mean, that's how, what is the purpose of the membrane, right? Tanmay, Rushi, Saksham. Okay, time to time maintenance of the membrane to remove the deposit. Okay, okay. So let us just have a discussion on this. See, yes, I see that's part of that. How do you think of a system? And normally, this is what we do for heat transfer based systems, that we try to do some maintenance or cleaning of the surface of the equipments, right, to remove all these scalings and foulings. But that is something we do once the performance of those units has decreased significantly, right? And there is a significant layer of these deposits have formed. But in the case of membranes, even very small amounts of these solutes, forming a layer over these surface would create a huge resistance to the flow, or its net permeability would reduce to a significant level. That is one thing. Second thing is that if these deposits are not cleaned almost like after one operation, it's not even periodic maintenance. I'm not talking about a scheduling kind of thing. Even after one operation or one experiment or one cycle of the system, these would also create, or this would also cause irreparable or irreversible damage to the membranes, right? Considering these membranes are mostly polymeric types, they would also cause these corrosive scales. So these, whatever these scales or the deposits that we are talking about, it's not the scale here though, it's the deposits that is forming, would also create irreversible damage to the membrane. Like for example, if you are talking about bioseparation or trying to separate some biological contaminants, right? You cannot wait to form a significant scale to do a periodic maintenance, right? They should be cleaned almost like after the operation or maybe during the operation. So that sort of idea, even though it is also to some extent it is proposed in many cases, but that doesn't prove to be quite beneficial, because this periodic maintenance or this periodic cleaning is so frequent that it needs some alternate methods. Like it is become so frequent that adds cost and shutdown of the system. Okay, so it has to be done so periodically, and this periodic dependence is so frequent that often you will have that the shutdown period of the membrane is almost equivalent to its runtime, and that is not a good way for engineering operation, isn't it? You will need to have some shutdown time of the equipment for this scaling, to remove these things, right? That is what we normally do for these heat transfer equipment, heat exchangers, cooling towers, and distillation column and all. And they are done like over 3 months, 6 months, or over a year or something like that. But in the case of membrane, if we think of cleaning them after so long time, it will become almost like unusable at that time. So it has to be done very frequently. So that's the reason the shutdown time would be significantly larger. So that may not be one idea. The common strategies that some of you also tried to suggest is some sort of flow. And yes, and this is something which we also tried to highlight in possibly the last class, where we said that the flow or the transverse flow over the membrane surface creates some convection on the surface of the membrane, so that these particles are removed beyond a certain point, and the growth of the formation of this gel or whatever this concentration or the formation of this highly concentrated region can be reduced because of the transverse action. It's like soil erosion kind of thing. Like you have a transverse flow over the membrane surface, so that any deposit that is present is actually scraped out because of the flow action, right? So that is one technique. So passing fluid in the opposite direction is not something I got it, because the fluid will be flowing in one direction, right? And so you want to have two opposing fluids, and how does this work?
So maybe applying pressure in the opposite direction.
From the filtrate side, you mean? Back flush kind of thing?
Yes, sir. From the filtrate side to the feed side.
Right. So that is also another technique. I mean, that is how generally the cleaning is done. Right. So that I would treat as a sort of cleaning idea, because normally you do not clean the surfaces of these membranes using a scrubber. Right. So let us say if it's a hollow fiber membrane, you cannot even access the inside region of the hollow fiber. How do? You do a back flush. You apply higher pressure on the shell side of the flow, so that the flow now penetrates from the outside to the inside core of these hollow fibers, and in the process any materials which got stuck over the surface will be dislodged and goes into the flow. So that is how the generally cleaning is done. But that is a process that you need to do, and all cleaning process that we can think of can only be done after the experiment or the this operation is over, right? But what we are trying to think during the operation, right? During the operation, what modifications could be done to the system so that these phenomena can be removed, not after the process, right? So during the process, as you know, there is a flux decline of the process, right? So I want to not have so much decline of the process, right? Even though I know that it will do, even if I start with a completely new membrane, I still do not, I want to reduce this, decline behavior less. So one thing is, of course, the flow. And if you increase the strength of your flow or the Reynolds number of your flow, in the case of this cross flow action or the transverse flow, that would reduce the impact of the fouling. Some other methods even with flow could also be done. For example, pulsating flow. Instead of a continuous flow, if you have like, a sort of flow in the pulses, that has been found to have more prominent effect in dislodging these particles instead of a continuous flow. So pulsating flow is one thing. Another important thing is that you can modify the surface of the membranes. Typically, most of these solutes or molecules are hydrophobic in nature, right? So if you increase the hydrophilicity of these membranes, right? So it would attract the water molecules more compared to the solute molecules, or the preference of the solute molecules sitting over the membrane or a hydrophilic surface would be less, and that would reduce the fouling. This is another strategy which has been also adopted, is to coat the membrane surface. The membranes are generally of a polymeric material and is highly hydrophobic in nature. All right. So if you and the contact angle is more than 110, 130 like that, right, degrees. So if you want to coat this with a hydrophilic material or some sort of hydrophilic behavior, then you will see that the contact angle is much less, 10 or 20 degrees like that, right? So then it is more likely to have the water molecules coming in its vicinity rather than these hydrophobic molecules. So that would to some extent reduce this fouling effect. Another thing that is generally done is to actually, I mean, that also depends on the nature of the solutes, is that you apply some electric field. Generally, this is applicable more for, again, for smaller sized molecules, because generally the smaller sized molecules are of charged nature, whether it's a protein, whether it's some salt. So there are charges in the system, right? So if you apply an electric field, maybe to get and give you an idea, let us say this is a this is a, let us say this is a plate, and over which you have a membrane, and on the top side also you have another plate. So the flow is in this direction and permeation is in this direction, right? So this is the membrane, right? So as along with the flow, the solutes get deposited more over the surface of the membrane, and let us say the solute molecules are negatively charged, right? So if I apply a positive potential here, plus volt, and a negative potential on the bottom plate, so there is a electric field, there is a electric field that is set up in this system, and that would try to drive these, sort of negatively charged molecules or charges in the systems towards up. So if it gets dislodged or gets moved towards up, we will see a net increase in the flux with the application of the electric field. Right. This is generally another strategy to use an electric field. I will talk about one more strategy and then we'll stop here, or maybe one more thing before we stop. Another thing is that, so this is generally called electrically enhanced filtration. All of you are aware of micelles, right? Isn't it? Micelles are formed by aggregation of surfactant molecules. So depending on whether the surfactant is placed in a water system or it's placed in an oil system, you can have the formation of the micelles or the reverse micelles, right? So typically the surfactant molecules, the head is generally what? Hydrophilic or hydrophobic? You have a head and a tail region, right, for surfactant. Generally the head is hydrophilic and the tails are hydrophobic. So in the water, to minimize the chemical this minimize the free energy of the system, they, if their concentration exceeds the critical micellar concentration, they will start to form these sort of spherical aggregates, right, where all the hydrophobic regions or the tail regions would be inside and it is covered with the cap of the this head region, which is exposed to the water molecules, right, because they are hydrophobic. So this is how the micelle is formed, and these micelles are of significantly larger size. Typically a micelle size is around 3.5 to 4. The diameter is almost like 4 nanometers. That's a significantly large molecule compared to the the size of, let us say, a sodium chloride molecule, or just right, the sodium chloride molecule size is almost like less than 1 nanometer. It's around 0.2 or 0.3 nanometer. That's the size of a sodium chloride molecule. Water is 0.3 nanometer, whereas this is around like almost 10 times of 20 times higher. It's around 3 to 4. So this is the size of the SDS, sodium dodecyl sulfate surfactant micelle. If it's you are talking about even larger molecules can also have a large size. Also aggregation number is another thing, how many molecules or how many surfactant molecules are aggregating, or monomer molecules are aggregating to form this micelle. So typically this is around 40 to 50 for the aggregation number for SDS molecule. It can be large also. Anyway, so these micelles are typically large particles or aggregates that form, right? Now let us say you have a system where you want to remove a very low molecular weight solute. Let us say copper chloride, and I want to remove the lead nitrate, right? And I want to remove this lead nitrate compound. because lead is very toxic, right? Now, lead is a heavy metal and it's also generally present in the ionic form, and its ionic radius and all is very small, less than 0.5 nanometers, right? Then to remove this, I need RO grade membrane, and RO itself is very low permeable thing. So the flux in a RO membranes is very low, right? Because it is very non-porous, of the very small size that could screen out these small particles. So what you could do is that this lead molecule is, or this dissociated lead ion is positively charged, right? And generally the surfactant heads, this anionic surfactants, which is SDS, has negative charged on their head, right? So SDS is sodium dodecyl sulfate. So the sodium part immediately gets dissociated in water, and it's dodecyl sulfate, which is sulfate is a negative group. So entire head region is a negative group. So this entire whatever the stuff that you have, the micelle is highly charged and in a negative way, right? Its surface is negative. So this is a positive thing, and this is a, since this we are talking about an ionic surfactant, it is negatively charged. So this will get immediately attracted and attached to the micelle, right? Now whether it will be placed on the surface or a little bit inside or to the core, generally it doesn't go into the core unless it's an organic molecule. It doesn't go inside the core, right? This sits mostly on the surface of the micelle. So it will get immediately attached, and this is by electrostatic attraction. So this is very difficult to separate. But what we can get now in the process, we get a lead micelle complex, and that is of very large size. So to remove this lead, this micelle complex, you can have a more open membrane. Let us say I can operate with even with a microfiltration membrane. So if I use a microfiltration grade membrane to separate this lead micelle complex, I will essentially be separating lead. That's my target. See, surfactants are very cheap, right, in the solution. So in the final filtrate, we will be getting, and the surfactant micelles are very large inside. So even with microfiltration, or let us say ultrafiltration, you can remove the surfactant molecules or these micelles, right? So entire lead micelle stuff will be removed. Okay, so using this strategy, instead of using a RO-based membrane, I use a more open system like ultrafiltration membrane, where the flux is high because the permeability of these ultrafiltration membranes are high. So I can use this, right, to remove lead, but in a slightly different way. Not directly we are removing, we are attaching or binding it to another binding agent. In this case, this is the micelle, and we remove the surfactant lead complex together instead of removing the lead individually as an ion, right? And of course this process will have a significantly higher flux per unit pressure drop than this what do you call for a RO based process. This is another technique where even changing the system by binding with a complex setting agent can also lead to higher flux in the system, and that would significantly save. So the cost that you save, or the cost that you incur here by addition of the surfactants in the system, and surfactants are not only cheap, they're also easily soluble in the system, right? But whatever, even if it's cheap, it do have some cost, right? Whatever the cost that you incur due to the surfactants is significantly lower than the energy cost when you talk about using a RO-based membrane to separate lead. So you will ultimately gain in this process. So we'll stop here for today. Again, we'll continue from here in the next class on the Friday, and we'll talk about more on this theory of the membrane separation process. Okay, thank you guys. We'll stop here for today. Enjoy the rest of the day.